Carl writes industrial control software in C and C++ to control large fruit storage machine. And he's been working between academia and industry for well over a decade. And he learned Python in the days when Python version 1.1 was around in order to assist with his PhD. And today Carl's going to talk to us about Goto Python. Yes, really. So let's welcome Carl Cerecke.
Thanks, Puppy. Actually, it was Python version 1.5 that I learned, not 1.1, in case you think I'm really, really old. Yeah, I've written a module which will let you do Goto in Python. And it occurred to me a couple of weeks back that actually there's some of the younger programmers don't actually know what Goto is because they haven't seen it before. I was quite astounded when I discovered this. So I'm going to take you on a little bit of a history lesson. This is how I learned to program on a Commodore 64. Have we got any Commodore 64 veterans? Yeah, oh, a couple of old guys up the back. Yeah. So this is how we did it back in the old days. This is a 4-line program to print from 1 to 10. Each line is numbered. You've got line 10, line 20, line 30, line 40. And you can see that BASIC in these days, they weren't big on white space. In fact, if you type your line in with white space, when you do a list, it'll just condense it all up. So we've got if n is less than or equal to 10, then go to 20, go to line 20, and then print the next thing. It's a jump, right? Goto is just a jump. I want to jump from this point in the code to somewhere else. It's been around a long time, right? In the beginning, when computers were first created in the 40s and 50s, they had this Goto, they had this jump. And in 1958, this guy, Heinz, well, they were in a pre-Algol meeting. Algol is a programming language which was created in 1960. So in 1958, they were still trying to figure out what it's going to look like. Now, to give you an idea, in 1958, the only other language really that was around was Fortran, which was created in 1956. Lisp was still in McCarthy's head. It was basically, I think he'd published a paper, but that was about it. It was just an academic curiosity. An old guy, a grey beard, is shaking his head. I've got the date slightly wrong, but that's about right. There wasn't any code written for Lisp in 1958. The first Lisp implementation was about 1960. And also Grace Murray Hopper and her team were thinking about what they were going to do with COBOL as well, and that there was no implementation of COBOL. So this is really early on, and Heinz here is saying, yeah, I don't know about this Goto thing. Maybe we shouldn't put this in here, which is quite, I'm just flabbergasted basically that this guy in 1958 is thinking, oh, this is a bit dodgy. So then in 1968, there's this famous letter to the ACM magazine by Edsger Dijkstra, and Goto considered harmful, and this is kind of started the considered harmful meme, I suppose, with articles, and that generated quite a bit of controversy at the time, and he basically said, you know, Goto's pretty bad, and so fast forwarding a little bit further, 1974, Donald Knuth, he is probably the greatest computer scientist arguably alive at the moment. And he was saying, well, structured programming, you can do it with Gotos, you just kind of have to be a bit careful. He kind of had a balanced approach. And then we started getting ridiculous. Goto considered harmful in 1987, and Edsger Dijkstra considered harmful. Someone wrote an article. That's pretty cruel, isn't it? There was even a delightfully contradictory article called "Considered Harmful Essays Considered Harmful." So that's a short history of the Goto. So why would we want to add it to Python? Well, I write C and C++ code for a living, and if I want to do something for fun, I'll do it in Python. So I don't work in Python really. It's just fun for me, and I thought it would be quite a good idea. But it turns out it's actually quite useful. So the thing that got me back into this sort of thing was I was trying to do a state machine to parse Bible references, which are kind of simple, so you don't need a full-blown parser, but they're kind of complicated enough that if you try to do it with a regular expression, you're going to come up with something really nasty. Nastier than usual for regular expressions anyway. So also, if we've got a nested loop, you've got a for loop, inside a for loop, inside a for loop, and then you want to say, all right, well, I've found what I want to, and now I want to jump out. That's another useful thing for Goto. Also, if you're writing a program which writes another program, having a Goto in the target language can be really useful. And lastly, if you've got an old program which has got lots of Gotos in, and you're translating it into Python, then having a Goto in your target language again is really useful. Now, the module that I've written, out of all of the uses, all of the people who use it that I know of, both of them were translating Goto into field code into Python. It's already been done before, actually. Some guy did it in, he wrote a Goto module in Python. Note the release date. It does actually work, but it's not really usable. It uses sys.settrace, and that is primarily designed for debugging Python, and it runs a little bit of code before every single line of your program to do your sys.settrace. In his case, it was checking for whether there's a Goto or a label in there. Really slow, so not much good. And I thought, there's got to be a better way. I thought I might as well have a crack at rewriting the bytecode of a function so that we can do Goto. Incidentally, we don't do Python at work, and I got this talk accepted, and I said to work, I said to my boss, look, do you mind using a bit of the training budget to help me pay for some of the costs of getting down here? And he goes, oh, what's he talk about? I go, I'm doing dynamic bytecode manipulation in Python, which is true. It just sounds a lot fancier. So I could have titled the talk that, and maybe I might have got a few more people, but go to it is. So Python, when you run it, it compiles into bytecode, and then it runs the bytecode on a virtual machine. Each bytecode instruction is about 1 to 3 bytes long, and these bytecodes, you've got jumps in there already, right? We've got jump forward. You can jump forward 5 bytes to that instruction. Jump absolute, I want to jump to instruction at byte 24, and you've got a bunch of exotic jump if false or pop. I don't know what they use that for, but I'm sure there's some good use. The dis module in the standard library is the one you use for disassembling functions. To have a look. So this is what I wanted. This is what I wanted the Goto module to look like. At the top, from Goto, import Goto, and then we've got a Goto decorator saying, which basically says, all right, this function is going to be using Goto. And I'm jumping over the print statement in there, just as a little test function. So if I call simple with an argument, it shouldn't print anything. It should just go to the end and then be all done. And we can have a look at the bytecodes, and we'll do that in a moment. But we'll look at the bytecodes when it's not decorated. So this is if you just had a normal function without the Goto module. And this is what it looks like. at the top, you can see actually it thinks that, so on the left we've got the line numbers, and here we've got, this is the index in the byte string. This is the opcode itself. And at the top you can see it thinks that Goto is a global variable, which it is, because we did from Goto import Goto. And then it thinks skip is an attribute of Goto. It's because we did Goto.skip, right? And because we're doing Goto.skip, it thinks it puts the value of whatever Goto.skip will eventually be, and then it puts it on the stack, but then it doesn't use it, so it does pop top to take it off the stack again. So what we wanted, our label is the same thing. It compiles to the same thing. So up there at line 302 there, at byte 0, we want to change that into a jump forward to 24, because that's where we say, okay, this is our implicit return none. And our label, we don't want any of that code in there, we just want to put that a whole bunch of no ops. Right, that's basically just what I said. And this is what we want it to look like. So line 302, there's actually 7 bytes for that, but we're only using 3 because we've changed that to a jump absolute. So there's 4 bytes that are just sitting there doing nothing. So I'll just put cross them out so you can see that they're never used. We've completely no-opt out our label, and that's what we want. So how do we do that? What does the decorator look like? And this is a very high-level view of the decorator. Fn, that's our function that we're decorating. We can pull out the code object from that. And that code object, as well as it's got a bunch, it says what all the globals are and local names are and so on. And it's also got this byte string, which is the co_code. That's the byte string, that's the opcodes that we want to change. So we dig in there, find all the labels and the gotos in that byte string. So we've got to take a copy of it and convert it into a list so we can modify it, of course. And then we know up all the labels, work out where all the gotos need to jump to and point them to the right place. Then we make a brand new code object, which is identical to the old code object, except it's got our sneaky little wee modified code byte string in there. And then we just return the function. And that's, in some ways it's a bit easier than a normal decorator because you're actually returning the same function that you're decorating rather than a new function. There's a few problems with this though. So consider this snippet of code here. We jump out of the loop. Now, it happens that in Python, when you start a loop, it puts a block. It's got an internal block, and if you on a stack. And if you, in that loop, go into another loop, it puts another block. And when the loop's finished, it pops these blocks. Now, if we jump out of the loop, but forget to pop the block, it'll just keep on pushing things onto the block because we're basically going into the loop a bunch of times and it never pops anything off. And once we get to 23 loops, then Python will quit with some exception. So we've got to figure out a way to make sure we pop the block. If I just go backwards a moment. So here, actually up the top there, see we've got those 4 extra bytes, and so we can work out, depending on how deep we are and how many loops we have to jump out of, we can put those pop blocks in there before we do the jump absolute. But we can only do a maximum of 4 because that's only that is only how many bytes we have available. On the other hand, if we jump into a loop without doing anything, without entering the loop properly, if we just jump into with a goto, it gets to the end of the loop, it tries to pop a block, there's no block to pop, and that causes a segmentation fault in Python. but we shouldn't be doing that sort of silly stuff anyway. So it takes, the Goto module takes care of all of these problems for us. And it also makes sure that we restrict a Goto to within a try block or within a with block. No jumping into a with block or jumping out of a try block or a finally block. Any of that sort of stuff is going to result in badness, so we don't do it. So, I mean, is it any good? There's not much point if it's really slow. And here I've got an example of a state machine for counting up to, I think that's 100 million. We are out of time? Give me about 4 or 5 minutes, and then we'll, because I think on my, is it 10 past 5? Finishes at 5:10. Yeah. All right, so I've got a wee bit of time. Okay. Right. Yeah. So with the state machine, we've got, if n is even, it's in the even state. We add 1, it goes to the odd state. Add another 1, it goes back to the even state. In the even state, it checks also to see if it's at 100 million. If so, then we quit. And that's our state machine. Not very exciting, but it's great for doing some timing. So I wanted to look at three different timings or ways of implementing this. One is a normal sort of way that you'd implement a state machine in Python. One with my Goto, and you can model this state machine with a while loop. So I wanted to do that as well to get some idea. Hopefully it'll be faster than the function-based one, but probably not as fast as the while loop. This is how, so if I ever have to do a state machine in Python, this is how I do it. There's a bunch of, if you type in to Google state machine Python, you get a whole bunch of libraries, most of which are total rubbish. If you want to do a state machine, you do it like this. I haven't really got time to explain that, but you can have a look at it later. It takes 35 seconds to do that state machine counting up to 100 million. Now, on the other extreme, we can model that state machine as a while loop. And that takes 11.5 seconds. And modeling it as Gotos, we can see that in the middle there, I've got a Goto state odd, and state odd's right underneath it, so I wouldn't have had to put those in there, but I wanted to model what it would actually look like if it was a real state machine. So I ran that through. How long did that take? 7.2 seconds. It's 4 seconds faster than a while loop. I was like, what? And so I measured it a bunch of times, It really was faster than a while loop. I thought, that can't be right. And so I thought, I'm going to have to go back and go back a little bit here and have a look and disassemble this while loop. Why is the while loop taking longer than my rewritten kind of bodged up bytecode? So I put this into a function and disassembled it with the dis module, and the bytecode was almost identical to my Goto one. And then I ran it again, and it turns out that when that while loop is inside a function, it only takes 7.1 seconds, but when it's outside a function, it takes 11.5 seconds. I have got no idea why. If anyone knows...
you don't get bytecode compilation in the outside scope of a Python file if you just run it. You don't get compilation to import or define a function.
All right, well, there we go.
So you didn't actually have any bytecode to start off with.
But it must compile it to bytecode to run it, right?
Yeah, but on the fly.
On the fly, okay. Yep, fair enough. Yep, yep. I figured it was something like that, but I didn't look into it long enough. But in any case, this result's pretty good, 7.2 seconds versus 7.1. If you look at the bytecode, it's pretty similar anyway. And that is the Goto module. Any questions?